suppose these two switches were working, 1 and 5th. Now one switch got damaged. Let's suppose 5th is damaged, right? I will come one by one. So if 5th is damaged, the operation will be continuous because you are getting the positive current. So initially these two switches were sharing the current, but now only current is passing through only switch 1 and it is coming to the load and going back through this B. So they're completing the path, right? So this converter, now you can see only two switches are conducting. In case of 120-degree mode of conduction, the two switches are conducting in that operation. So this converter will be shifted to 120-degree mode of conduction. In 120-degree mode of conduction, the operation is just reverse. Means the voltage which we have here as a what we can say phase voltage, that we get the quasi square. However, the line voltages which we get, that is stepped in. So operation, it may be possible due to failure of switches. The line phase voltages may be quasi square because now the converter is switched in a 120-degree mode of conduction because switch 5 is going to be failed. Now let's suppose one down switch is failed. So what will happen? If down switch is failed, there is no return path which will return the current to the supply. You can see both these terminals, the switch 1 and 5, both they are connected with the positive DC bus. But there is no switch which are conducting, which will supply or return the current so that the circuit can be completed. If circuit is not completing, no voltage will appear at the outside, simply. So minimum one switch at the upper side and one switch at the lower side, they must conduct, otherwise inverter operation will not take place. I hope I answered your question.
Between 120-degree conduction and 180-degree conduction, which
so in 180-degree conduction mode, what we have realized, we have switched the switch till 180-degree. What we have to do in case of 120-degree mode of conduction, we have to switch the first switch till 120-degree. That's all. That is the main difference. Because as the 180-degree mode of conduction means one switch is conducting for 180-degree. If I'm saying 120-degree mode of conduction means one switch is conducting only for 120-degree. Yes, sir. Any other question? 120-degree mode of conduction. I hope you understand. I hope you understood what I was telling. Right?
Yes, sir.
So
I understood, sir.
Yeah, 6 switches are there, right? So I have to take these 6 sections. But if I talk about S1, S2, S3, S4, S5, then they will conduct for 120-degree. So if I talk about S1 will turn down till 120. So S2 will start at 60, but it will be on for this 180-degree only, right? It will start from 120, and it will be on like this. It will be on like this. The last switch, it will be on in this fashion. Are you able to get it? So the switching sequences are going to be changed, whether we are talking about 180-degree mode of conduction or 120-degree mode of conduction. Right? So if someone is asking, suppose I am operating my charger in open loop with the till now this type of operation, I would I told you for conversion, but generally PWM converters people are preferring. But if somebody is asking, suppose you are connecting a charger and the voltage which you are supplying, this charger is the inverter of the charger, it is operating in 180-degree mode of conduction. So the line voltage will have more harmonics, or your phase voltage will have more harmonics. So you can see I have studied this 180-degree and 120-degree mode of conduction. So I can quickly answer. The phase voltage is quasi square in shape. However, line voltage was stepped wave, and the line voltage was quasi square in nature. So this stepped wave is more closer to the sine wave, so it will have less TSD as compared to quasi square wave. Now what I'm going to do, I'm taking a 15-minute break and see you after 15 minutes. Wired, wireless, and then the third one which we are going for, the battery swapping. Why the battery swapping is not so popular? Because let's see what is battery swapping first. Battery swapping is a technology that allows electric vehicle to quickly replace their depleted battery with a full charge one at a designated place or designate. And now let's start our discussion. So we discussed this particular topology here. This particular, conversion from DC to AC, and earlier we discussed the conversion from AC to DC. So both ways are important here for conversion from one quantity to the another quantity. Now let's see what are the other type of techniques which are there after the charging the battery from the plug-in charging or wireless charging. Third one is battery swapping, right? So we have the wired-based charging, wired-based. The second one, which I told you, wireless.
The screen is not visible.
Okay, just. Okay, sorry, I have not shared this screen. I hope now it is visible. Wired wireless, and then the third one, which we are going for the battery swapping. Why the battery swapping is not so popular? Because I mean, let's see what is battery swapping first. Battery swapping is a technology that allow electric vehicle to quickly replace their depleted battery with a full charge one at a designated place or designated battery swapping station. Right? Instead of waiting for vehicles battery to charge like 25 minutes, 6 to 7 hours, we at the charging station as a designated place, we have our charge batteries, and each charge battery can be replaced with the empty battery. Right, discharge battery. Driver can exchange the entire battery pack for a fully charged one, significantly reducing the time required for recharging. So it is a kind of petrol pump where you are going and refilling the fuel in the empty tank. That's all. So you are removing the discharge battery and recharging it. I mean, plugging the charging battery. But the question is, how much feasible it is, right? So it is feasible for where we have one battery pack or only one single battery pack which is there in the two-wheeler or even three-wheeler. But if you talk about the very high power density batteries on where downside we have seen the downside everywhere they have put this battery bank, and that is very high power battery. So in that case you need some kind of support. Alone you cannot change it, right? As well as they are connected some type of connectors, so you have to remove the connectors as well from the terminals. So in such cases, this battery swapping become quite difficult. But where we need to change the battery pack of one or two, that could be easy. But for a battery which is having a huge, huge pack, or this number of packs are there in a series or in parallel, so that we can make a one big battery. So that would be difficult in such situations, right? So key characteristic of battery swapping: quick exchange, depleted battery replaced with fully charged one, right? The charging time could be less. Automated process, station use automatic systems for battery exchange. Modular design, EV use easily removable and replaceable modular battery pack. Charging infrastructure, swapping station stock press charge batteries, right? Reduced downtime, minimizes vehicle waiting time, improving utilization. And application suitable for high mileage commercial vehicle. So advantage: quick recharge, reduced charging infrastructure, right? There is no need to install the onboard like the charging stations where we can see huge connectors we are taking from one end to another end. Increase vehicle availability, eliminates range anxiety, right? So if we have battery swapping stations in a highway, so in after let's suppose 10-20 kilometers, we can install these battery swapping stations. So range anxiety can be, you need not to carry a big battery, because after 20 kilometers or 30 kilometers I will get the battery swapping station where I can change this battery, right? So offer a solution to address range anxiety by enabling quick range extension. Disadvantage: infrastructure investment, right? You have to put, as the battery has a fixed cycle, right? Fixed time period, whether you use it or not use it. So within a 3 or 5 year, whatever the life of the battery, that would be, it would be discharged. So what we have to do, we have to take care of this kind of infrastructure where, we have to invest more in such infrastructure. Establishing battery swapping stations requires significant investment in infrastructure and battery inventories. Standardization, need to develop some standardization for battery swapping. Till now, there is no standard, right? And it is very challenging to change these or swap these batteries for a huge vehicle. Where this, like suppose if I'm talking about the exchanging of battery or swapping of battery for a truck, heavy duty vehicles are there. So it is very challenging to change these batteries from, swap these batteries from empty with a fully charged battery. Limited applicability, best suited for specific use cases like fleets with predictable routes and high daily mileage. Operational challenges: ensuring smooth and efficient battery swapping processes, which is essential in this case. So smooth and safety is one of the major concern in case of battery swapping station, right? Suppose some person who's not knowing these things, technical things related to the, safety and other features. So this may harm if you are touching the battery without switching off or taken out from these terminals. So that thing we have to take care. So operational challenges are there. So under operational challenges, the swapping of the battery is also coming, right? Swapping of the battery, it is under the operational challenges. So definitely there are operational challenges if you talk about the battery swapping techniques. So charging standards and plugs, we have safety, reliability, user friendliness, power level, and charging times, communication, and standard compliances. So you can see the basic structure of this charger. basic structure of a charger. So we have AC, whether you can go with the AC of 50 hertz or 60 hertz. Accordingly, you have to select the voltage 110 or 120 or there's 230 volt. Then we have rectifier and filter. So filter, basically we are talking about the DC bus capacitor, and here input side we can use input side inductor filter. So if you talk about the rectifier could be a simple. If it is a one unidirectional charger, the current is flowing one way, right? So this rectifier could be your direct rectifier. Otherwise, it has to be modeled with the control switch. After this DC bus, what is inverter? Inverter I already told you, right? So we have. Sorry, this should not be short circuited. We have this switch. And this one, right? So from prime, so this inverter is connected with the. So what is HF AC? High frequency AC, right? And we have, depending on the battery size, we may have 1:2, or there are different duty ratio or different these winding turn ratio can be used here. So here, what we can do from A to B, we can connect one winding like this, and then we have another winding which is further converting this high frequency AC HFAC into DC by having a rectifier. So in case of this type of charger, onboard charger, after this rectifier, right? What you can realize, these things are common. We have inverter and we have rectifier, and this rectifier again it is converting this high frequency AC, right? High frequency AC into DC. Right? So both ways we have onboard or offboard charger. So onboard, if you talk about onboard charger, this particular part is there in the car. So only 2 terminals are available, or 3 terminals with the ground or on safety neutral point of view. We can plug in this directly to the AC. But if we talk about the offboard charger, these all things are inbuilt in the charging station, starting from here to till this point, right? Apart from the battery. So onboard charger, all these things are inbuilt in the car. However, onboard charger, all these things. Yes? I could not get it. What you are saying?
What is HFAC?
I told you high frequency AC means these inverters and rectifier, they are fired at very high switching frequency. Why we are going for higher switching frequency? Well, a high frequency AC signal. Why? Because the if you see the size. So if I talk about this inductance, so L is proportional to switching frequency. Inversely proportional with the switching frequency. So if I'm going for a higher switching frequency, the value of inductor will be lesser. Right? Suppose if I'm talking about this switching frequency, suppose is fundamental, 50 hertz. So what would be the size of inductor? It will be large. If the switching frequency is 10 kilohertz, so the value of inductor will be small. Are you able to get it? What I'm saying? Correct? So that's why the size of this transformer we wanted to reduce. So high frequency transformer, you might have seen, they have very less size as compared to 50 hertz transformer. That's why people are going with the high frequency AC transformer, so that the size of the transformer can be reduced. Able to get it?
The transformer will reduce the frequency.
No, transformer will not reduce the frequency. The size of the transformer will be reduced by selecting a higher switching frequency to fire these switches. Which we have inverter and rectifier side. Correct? So if we generate high switching frequency waveform here, the size of the inductor will be less. Because inductor size, it is inversely proportional with the frequency. If I'm choosing a higher switching frequency, my inductor size or the transformer size drastically decreased.
Sir, one is question there, sir. Mm-hmm. In the primary side, suppose 10 kilohertz is there, but outside of the secondary side, how much frequency will the output?
Which side? Output at the DC side you are talking about?
Output side.
Output, which output? You are talking about this output.
Secondary side, that means that battery will connect.
Yes,
sir. Yes, sir.
Yeah, so see, here the magnitude of voltage will change because you have taken 1:2 ratio, but there is no change in the frequency of this waveform. Frequency of the waveform will remain same because it is a transformer. Right? There is no conversion circuit. Try to understand, frequency is not going to be changed in the transformer. If you are having a 50 hertz transformer, voltage can be increased and decreased, V1 and V2, but frequency of operation will remain constant.
Yes, sir.
So how you can change? Yeah, voltage. So frequency will not change.
Yes, sir.
So whatever frequency you have chosen, according to that frequency, you have to design the inductor. I hope I have given the answer.
I have seen that Nexon EV charger. So it is a quite heavy charger. Means some circuit is inside that charger.
Yes, so that is onboard charger, right? Onboard charger. That's like, yeah.
What are the components which is shown in this?
So whatever the charger I'm showing here, that are the components which are included in.
All are there.
Yes, inverter, rectifier, it is high frequency transformer. All these things are there.
It is also inside the charger.
Yes.
So transformer must be need some cooling also, no?
Right, so cooling they have provided. I mean, some air-cooled transformer are also coming into the market. Need not to have oil-cooled or some other cold, but air-cooled transformer are also there.
Okay, so full all this circuit is inside charger only.
Yes, inside charger. So here I have shown in terms of block diagram, but you will find out a single PCB can contain all these components: inverter, rectifier, mounting of the transformer, and then this front-end rectifier.
That means our battery will charge from the rated frequency.
Sorry about it, but DC does not have any frequency.
No. DC has no frequency. Yes, sir.
Yes. Yeah.
Ripples are there.
Yeah, ripple will be there because you are converting this high frequency AC into DC. So higher ripple will appear toward the battery. People are working on different technique to remove the ripple which is going to the battery through control or through some circumstances. Yeah.
Size is inversely proportional to frequency that is based on which formula, sir?
Current? I didn't say current is proportional to frequency.
No, size
Size of the inductor, you will have design of different converters. Design of this, if we talk about design of boost converter. So what is the inductor? What is the boost converter formula? Do you know? Inductor design of boost converter. Can you go to the inductor design formula? What is this inductor design? L. How do we write L? Value of L. C. Output capacitor design. So L boost or L, that can be defined as a even though duty cycle, if I'm not wrong, D input voltage, and then we have switching frequency multiplied by ripple in the current. So this is the formula which we are following. So L you can clearly see L, if other things we can keep constant, L is inversely proportional with the switching frequency.
Sir, L is equal to N5 by I.
L is equal to
N5 by I.
5 by I. What is that?
Turns into flux divided by current.
But here we are talking about the switching frequency, not your fundamental frequency or the flux which is linking with the N5. Right. Here we are talking about the what is the basic relation between inductor and switching frequency. That's all. So this way we can design this first system. Now let's go to the basic charging topology. So this is already I have shown you. Now in case of off-board charger, right? If I take this topology, so you can see the only difference is the fast DC charging system, the off-board is conductive AC, right? So this is installed till this point, and with the vehicle only this part is there. Only battery is there with the EV, right? Rest of the system, this system, it is installed in the charging station. Installed in the charging station. Right? So this is known as fast DC charging systems. Where this, however, if you compare this one, so this is the slow charger, onboard charger. So you can clearly now see the difference, right? In case of onboard charger, the rating of the charger is quite low. However, in case of offboard charger, the rating of the charger will be higher because it is installed at the charging station. So we can also use three-phase supply for that. But if you talk about the onboard charger, they are developed with a single phase supply. And again, we have wireless-based charging systems. Wireless-based charging system. This is the transmitter. And this is the receiver. This is a receiver. This is the receiver side. So receiver side, it is installed in the vehicle. It is installed in the vehicle However, this one is at charging station. So you can see only for this part we are talking about it is wireless, where we need not to plug any connector. But in actual sense, if you see at charging station, the rectifier and inverter, they are connected with some link, right? They have some wire-based systems where we need to connect these systems, and then we have to charge this particular. Because otherwise, how will you get the power? Power you will not get if you are not going to going with this. So a transmitter is at the charging station and receiver is at the this. Yeah,
Hello.
please go ahead.
Sir, from the wireless charging system, how much current will you get from the receiver?
It will depend what are the component which you have designed for. I mean, what are the component you have chosen? What is the rating of rectifier, inverter, whether they have been connected with the single phase supply or three phase supply. Suppose I'm saying it is connected with the single phase supply, so it is limited to 3.3 kilowatt, 230 volt. You can calculate the magnitude of current which is going from the single phase circuit. If you have a higher side like three phase supply, so three phase supply can give you some flexibility. You can design a 15 kilowatt charger, 20 kilowatt charger, and you can choose 415 volt grid, right? So you can calculate the current like 20,000 divided by root 3 into 415. So this would be define the magnitude of current from the receiver end, from the transmitter end.
This charger can be converted from low speed charger to medium speed in same charger. Is there any means in some cars? Is there any provision provided to change the speed of the charging in a single charger only?
Can you repeat the question?
Means can we have a regulator type of thing like we have fan we have regulator speed 1, speed 2, speed 3.
Yes.
Can we have in this charger to make it from slow charger to medium speed charger? Obviously,
So we have BMS, right?
Huh? Okay.
We have BMS.
Okay.
So ultimately BMS is nothing but whatever you are told, we can regulate this. So what it is doing, it is charging the battery with the constant current initially. Then slowly the magnitude of current is reduced. It is reached in the constant voltage zone. So till the time where the battery reaches to the optimum voltage, 12 volt or 13 volt, whatever you are considering, after this 12 volt, it will change into the voltage. So initially it will be charged with the higher magnitude of current. But later on, as soon as the battery is settling to the 80 or 90% of SOC, the battery current will be reduced. Same fashion. There is no change. Same pattern we are following. So for that, this must be integrated with the BMS so that they can give the communication to the rectifier or to the DSPs. Like now, we have to reduce the power. Likewise. Let's go to the next topology. So this is the small charger which people are utilizing. I would say this is the low power charger, right? And most of the time it is used in the laboratory, in adapters, laptop adapters, this adapters, mobile adapters. They are using this kind of topology. So we have AC grid here, the fuses people can take, and front end side we have this diode rectifier, right? So it is this one is AC, and once suppose this one is D1, this is D2, D3, and D4. So to get this AC, we cannot conduct both these diodes at the same time of the same length. So what we will do? We will take diode here and go back and go to the DC side, and then it will come from the D2 and we will complete the path. So when this switch is on, one switch you can see here. So this is flyback converter. Flyback converter, it is developed having a single switch and having an isolated converters, one diode and capacitor, then we may have this battery back, right? Battery. So if this D1 and D2 are on, right? Suppose the supply voltage VAC that is greater than the VDC. Keep in mind, diode will conduct when this VAC is greater than VDC, right? VDC, I already told you. This is the VDC, constant voltage. Now AC is superimposing on this voltage. So the points, these are the points where this current is flowing from source to load, because this is the voltage where the diodes are conducting. So if diodes are conducting that time, at the same time capacitor will be charged, but we wanted to push the power, we charge the primary inductor, and this inductive energy that has to be transferred to the secondary. So what we have to do? We have to switch on this S1, right? We have to switch on this S1. So if S1 becomes short circuited, what will happen? Anyone? If S1 becomes short circuited,